Okay, so we will continue the problem that we were doing, which is example 5.5. It's about Hubble Telescope. And the block diagram that is given to us is for the system that the Hubble Telescope is pointing towards. The input signal is the command in the direction in which the Hubble telescope should be pointing to, and the output is, of course, the actual direction in which it is pointing. So um, a few requirements of the system were given to us. The three requirements: the percent overshoot of the output to a step command maximum should be 10% or less than 10%. And the steady state error due to a ramp command, input ramp command, is minimized, and the effect of a step disturbance is reduced. So what we did is we did the first part, and we figured out that the value of the damping coefficient zeta has to be 0.5912 for a maximum overshoot of 10%. And it has to be greater than 0.5912 if the overshoot is needed to be less than 10%. Now, keeping the maximum value of 10%, for that value, we found out that the gain of the amplifier and gain of the feedback, K and K1, the values of the gain of the amplifier is K, and the K1 is the parameter associated with the feedback. So that the relationship between those two were that K1 is 1.2 times square root of K for 10% overshoot. So this we have already covered requirement number 1, or A. Let's look at the second requirement, that the steady state error to a ramp command is minimized. So let's go ahead and this is B. So input is a ramp command. Let's say input is T. That means the Laplace transform of that will be 1 over S squared. And we want the error to be minimized, so the steady state error to be minimized. So what we are going to do, we are going to write down the equation of the steady state error to a ramp command, again, assuming the disturbance is 0. So let's note that down, that the disturbance signal is 0. So the input is activated, disturbance we are assuming to be 0 at this time. So we know that we already have the transfer function right over here. This is our transfer function, K over S squared plus K1 S plus K. And if we go back, so the transfer function is K over S squared plus K1 S plus K. And the error, steady state error, is Rs minus Ys, or 1 minus transfer function times Rs, K over S squared plus K1 S plus K times, or 1 minus this, times Rs, which is 1 over S squared. Let's simplify it a little bit. Es is equal to S squared plus K1 S plus K, and that plus K and minus K will cancel out. So in the numerator, we're going to get S squared plus K1 S, and denominator will simply be S squared plus K1 S plus K multiplied by 1 over S squared. As you can see, S squared and S, they're common factors. So if we take one S out as a common factor, that S is going to be cancelled by 1 of the S over here. So my equation is going to be simplified to S plus K1 divided by S squared plus K1S plus K, and then 1 over S. Therefore, the steady state error using the final value theorem, limit s tends to 0, SES. Again, this S and this S will cancel out when I put ES over here. So I will be left with this term. And when I put S is equal to 0, all the S variable will become 0. So this S will become 0, this S will become 0, and this S. And I will be left with K1 over K. And that is my steady state expression. Based upon the value of K1 and K, we can calculate the steady state error between the input and the output steady state values. So that's my next requirement. The third requirement is the effect of the step disturbance is reduced. So first we are going to write down now the transfer function due to the step disturbance. And then we will calculate the error again between the input, which in this case we're going to take to be 0. We're going to assume to be 0 because we are only taking the effect of the step disturbance. So input command is going to be 0. But remember, the error is still measured. The tracking error is still measured over here. This is the tracking error, ES, which is RS minus YS. So the tracking error, that is not going to change. If RS is 0, we are going to put 0 for RS, and the error, tracking error, will simply be minus YS. So the step disturbance means the disturbance is a step input. So let's go ahead and figure out what will be the output, which is the effect. What is the output based upon the step disturbance? And then the negative of that output value is going to be the error, tracking error. So let's go and do part C. In this case, my TDS is equal to step, and I'm taking my input signal to be 0. Now, let's go back. So this is my G, and this is my GA. So if I'm writing my TDS, it's going to be hectic, but let me redraw it real quick. So this is my one block. So this is my summing amplifier. This is my summing amplifier. This is my amplifier GA, and this is, I think, K. I'm going to go check. RS in this case will be 0. And I have TDS coming here, which is step function. Let me go back a little bit. So amplifier gain is K, and then this is GT over 1 plus HGT. So this is G. And G is GT over 1 plus HGT. And I can write down the expression for that in terms of whatever is given to us. We did drive it, guys. Let's see. Did we drive it? No, we did not. Okay, so let's drive it real quick. So GT is 1 over S squared, and H is K1S. So GT is 1 over S squared, and H is K1S. So my G of S will be equal to 1 over S squared over 1 plus K1S. So 1 over S squared. So 1 power of S is cancelled by this. And G will be equal to, and then I have this S is going to cancel 1 power of S over here. So this S is eliminated. No, I cannot just cancel it right now because it's adding My mistake. I didn't see that. I have to first keep it as it is. S square. So one power is cancelled out. So I'm going to have S plus K1, and then I'm going to cancel that. So I will have 1 over S over S plus K1, which will be 1 over S times S plus K1. So that is going to be my transfer function for G, which is GT over H. GT being 1 over S square, H being K1 S. Okay, so now from this block diagram, this is my Y, this is negative, this is positive, and then this is all positive. This is positive, and this is positive. Positive, positive, and then this is negative. Okay, so let's go ahead and then write down again the expression for Y in terms of TDS, and that is going to be over here, you're going to have negative Y. It's going to be GA times Y. TD will be added into that. That's negative. Of course, Y is negative. So TD will be added into that. So that's going to be TD minus GA times Y. And everything is going to be amplified by G, which is this. And then Y. So let me write this down and then simplify it. So Y of S is equal to G times TD minus GA times Y. Okay. So Y of S, I'm going to bring this term on the left side, take Y of S common. So I will have 1 plus G times GA. And on the right side, I will have G times TD. So Y of S will be G over 1 plus GA G times TD. Let's go ahead and plug in expressions. G is 1 over S plus K1. 1 plus GA is K divided by S plus K1. And of course, TT is 1 over S. Let's simplify it. So let me put it in parentheses. S plus K is going to be cancelled out once we multiply this. So we're going to be left with 1 over S square plus K1S plus K times 1 over S. That is equal to Y sub S. So that's my Y sub S. Okay, so my error signal, which is RS minus YS, as we discussed, will simply be, since RS is 0, will simply be negative 1 over S square plus K1S plus K times 1 over S. And from that, my steady state error E steady state will be equal to, using final value theorem, of course, S times ES, limit S tends to 0. So this 1 over S and S will be cancelled out. And I'm going to put S to be 0 here. So 0 and 0. So I'm going to get only negative 1 over K. That is my steady state error due to the disturbance signal being a step response. Now, if you look at all three conditions, 1 over k, k1 over k, and the first condition was k1 is equal to 1.2 square root of k. If my k value is small, then the steady state error is small. K value is smaller. In this case, actually, if a k value is going to be small, my steady state error is going to be large. So let's look in terms of k1. Let's see if did we do it correctly, because we are not getting any k1 term over here. Let's see. TD minus GA. So GTD, GA is going to go 1 over GA. 1 over S times S plus K1. 1 plus K over S times S plus K1. S squared plus SK1 plus K. So seems like it's good. Seems like it is good to go. And we put A is equal to S is equal to 0. So this is going to be, and you're going to be left with negative 1 over K. All right, assuming it is good. So in this case, to reduce the steady state error, my K value has to be large. In this case, my K value has to be large in order to reduce the steady state error. And in the first one, if my K value is going to be large, then, well, K1 is going to be large as well. So we will have to see what we do. Let's go ahead and take a value. I think in the book, they're taking a value of K to be, if I remember correctly, to be 100. So let K is equal to 100, which will give us from A, K1 is equal to 1.2 times the square root of 100 is 10, so 12. So that's going to give you 12. And from B, if we keep K1 to be 12, then from B we will have 12 over 100. So steady state error is going to be 12 over 100, so 0.12, 12%. And this is for peak overshoot of 10%, remember. K is equal to 100 and K1 is equal to 12. And from C, of course, my steady state error will simply be negative 1 over 100 or negative 0.01. So these are my values. Now what we are going to do, we are going to plot both the disturbance, step response, the output due to the step response and disturbance when we have these K values and K1 values. And we are going to plot the response for the output for the input step response, the disturbance step response and input step response. And then we will see how do they compare for these K and K1 values. So we're going to go ahead, and we know that our transfer function, we have both transfer functions. We have the transfer function for Y for TDS, the step response. So that transfer function is, this is the transfer function right here for if my TDS is a step response. Actually, the transfer function is here. Sorry, this is the transfer function. Let's delete this. This is the transfer function. And of course, TDS is your input. So this is YS over TDS. And likewise, from the first one, we have transfer function, which is right over here. This is my YS over RS. Right here, YS over RS. So let's go ahead and plot both of them for the value of K to be 100 and value of K1 to be 12 and see how the response is going to look like. And if these values of K and K1 are good. So let's go ahead and do that. Let's show control. And first I'm going to define my system one. So let's call it Y. Let's call it system one, which is the first transfer function that I have. Let me do this first. Let me say K is equal to 100 and K1 is equal to 12. And then I'm going to write down my system. So system one is the transfer function for the first one, which is K over S squared plus K1 S plus K. So numerator is K and the denominator is S squared, so 1, and K1 and K. So this is my transfer function. And let's do system 2. System 2, which is the transfer function of my disturbance transfer function, which is 1 over S squared plus K1 S plus K. So let's go back. And my numerator is 1 and the denominator is same. S squared K1 K. So that's my next transfer function. And just by looking at the transfer function, you can see that in this transfer function, my gain is 100, and in this transfer function, my gain is 1. So you can see that already that my input response is going to be much larger than my disturbance response for step input command and step disturbance command. In this case, our zeta was 0.6 approximately. So if I want to plot it for 4 time constants, the settling time, so 4 times 0.6 is going to be 24, so 2.4 second approximately is going to be that time. If I want to do 2.4 is okay, I guess. So if I do, my time is 0.01 and 2.4 up to settling time. Let's so let's go ahead and first we have to do the step response or a step. So I'm gonna do my y due to r. So let me call it y. So y due to r is equal to my step of my system one, and I'm gonna put a time. I'm gonna plot against. I'm gonna calculate values against the time, so I can use the plot over the same time and plot both of them in the same graph. So this is my YR. And then Y due to the disturbance signal. So Y due to the disturbance signal, let's call it YD. That's going to be a step of system 2 against the same time. So if you put the time command or time parameter, it's going to evaluate that system for those time values. If you don't, then it's going to evaluate for default time. And now I'm going to plot both of them in the same plot. So T comma YR. And let me make it a little bold, line width 2. And then T comma YD, line width 2. Okay, so this is my response. Let me go ahead and put this in the notes as well. Let's go ahead and click this. And let's go ahead and put the plot as well. Plot. Plot, I can just, don't have to flip, I can just do edit and copy to clipboard and then put plot. All right, so we can see that the output, the y output due to the input for, again, remember k value is 100, k1 is 12. This is y t due to r t. And then, of course, this is y t due to the disturbance signal. So t t. So as you can see, for both commands to be input, TT is in, both commands to be step, TT is a step and RT is a step. Of course, your output due to the input is much more substantial than the output due to the disturbance for the value of k to be 100 and value of k1 to be 12. So good values. I believe you have 10% overshoot for the input. And the steady state error for the output is about, what was that steady state error? It's about 12%, I believe, right? Yeah, about 12% steady state error for the output due to the input command. Oh no, that's when RT was a ramp signal. Right now we're not plotting ramp signal. Right now the steady state error is 0 because it's the same. Output is 1 for input command to be 1. But if you plot for the ramp input, then the steady state error is 12%. But we are plotting, again, both signals are the step. And for the step command, of course, this is quite a smooth. Okay. So, and of course, you can see that this is, YT is a little bigger. It's not, so input is 0, RS is 0. And since YT has some value, and that's why you see here, our steady state error came out to be negative, because Y is, steady state value of Y is 0.01, as you can see from this curve. But the input is 0. So 0 minus 0.01 is going to have the negative steady state error, as you can see over. Okay. So this concludes this problem. We found the values of k and k1 per requirement, and we plotted both the output for both the step input and the step disturbance.